Okay, so I want to continue with what I was talking about last time, and I was trying to give you some overview and some background on this idea of jamming and where it's gone so far. I ended with telling you a little bit about the density of states and the normal modes. So let me, before I continue, are there any questions that people have on what we've done? No? Okay.
I have one question. So what would have been alpha value for all those P's that Clark used back in the day? Because it was like soft spheres, like how he would have modeled it.
I'm sorry.
The potentials, like, because alpha could change depending
right,
on soft spheres or whatnot.
And so for but who modeled it? Are you saying?
The guy who did
the P's?
Experiment.
So if you write at jamming, you don't care about alpha because there's no overlap right at jamming. So at that sense, I could have gone without worrying about what the potential is. It could have been a hard sphere or whatever. And so you're just trying to look at little perturbations around that hard sphere limit. But if, in the sense that P's are P's, they are kind of elastic objects, and so then typically the alpha would have been 5/2. That's okay. So let me. Okay. So what I promised that I would show you about. Oh, I guess I can't. Maybe I should turn this. Is the second one down? Is that getting clear? Okay, so what I promised I would show you last time, I didn't show you any of these images, is someone asked, or a bunch of you asked, what does a normal mode actually look like? And so this is a very, very low frequency. It's probably the lowest frequency normal mode in one of the packings that we have. And that's what this image is. Each dot is showing where a particle is. And the lines are showing what the amplitude of the normal mode is, the amplitude of the normal mode is on that particular particle. And so if this had been a plane wave, which is what you would have gotten for a crystal, you would have had waves of dark, light, you go through where the nodes are, where you just get the dots with no motion, and then you get the next antinode where it would be dark again with arrows in the other direction, and back and forth. And this is not what you get for these modes. These modes look more or less random in some way. That is, they don't have a nice decomposition into plane waves of any kind. And so this is one of the things that I decided I'm not going to go into this aspect of what we did, was to try to analyze these in terms of various kinds of take the Fourier transform of all of this stuff. You can do that, and you can look at the longitudinal component of this. You can look at the transverse component of this. And these, what you should get from a picture like this, and what the upshot of all of that kind of analysis is that what's really different about these modes from what you get in a crystal is that in a crystal where you have plane waves, every frequency corresponds to a wave vector, right? I mean, you have an omega versus k relationship. What you get here is that you have a well-defined frequency. That's the frequency of your normal mode. But then what you get mixed into it is all possible k's. That is, it isn't just some low frequency or some low k, some long wavelength mode that comes in here. You get the long wavelength, but lots and lots and lots of other higher frequency, higher wave vector components. And that's why you were able to get a density of states that looks like this. So this is what I showed you last time. I drew this picture as a typical thing on the board. So this is actually what the data looks like. So you saw this last time. So each one of these is for a different amount of compression. 10 to the minus 6 is the one closest to the jamming threshold, and that's this dashed line. You get to 10 to the minus 3, and you can see that you still get this plateau going down here, but it then starts to fall off as you get very close to zero frequency. Just putting this on a log frequency axis here, then you see that you really do get this nice long plateau that goes all the way down to zero frequency at the jamming threshold at phi c. But before you reach that, you, as you have more and more compression, you get this fall off that occurs at different frequencies away from that plateau. And so we would say, let's say for the blue line, this would be where it falls from the plateau. We call that omega star. And this is what I showed you. The last graph that I tried to show you last time was this omega star versus the compression. And this is for harmonic potentials. So these are just alpha equals 2, that is just springs. And these numbers are going to depend the fact that this is a power law here of roughly 0.5 that depends on what the potential is that I use, what the value of alpha. So yeah, Drew, here's. Yeah, so this would be down here. Yeah, so this is maybe even smaller than that. I mean, 10 minus, I mean, we had some things down 10 minus 8 that we looked at to really get close to see that this is the behavior. And so this is a typical very low frequency mode that is still extended. You can see this thing extended everywhere. If you really look in the tail of these things, if you have enough data that you go down into that regime, then you see that these things become quasi-localized, and that's what I also mentioned last time, and I will say a little bit more about that now. Right. So so this is what I didn't say explicitly, is that I ignored finite size effects in a lot of things, that is in the counting and so forth. Here is one place where you know that the finite size effects are going to play a role. That is, if I take a system, a box of any size, and I'm not exactly at the transition, not exactly at phi c, then I have this fall off here. This is these new anomalous modes that I have. But you then calculate what is the lowest frequency plane wave that you would have gotten into this box if you had talked about what the speed of sound is for the longitudinal transfer sound. And what you find is that if your box isn't big enough, you don't have a mode that's down here that you can see. And so these boxes are always, well, I will show you some data in the next slide that shows you, oh, you can begin to see plane waves in there, but they are not this continuum plane wave dispersion that we're able to get. Okay, so what I just want to say now is, so with this, okay, so you can talk about various length scales from this. So once you have an omega star, and you know that this omega star is going as, what did I say? This goes as phi minus phi c to the alpha minus 1 over 2. So this is what we find in the simulations. And so this just works out to when alpha equals 2, which is harmonic, this just becomes to the 1/2, which is what you saw there. Then you can define various length scales. That is, what is a length scale just from this omega star? You can say, well, okay, if I have a sound wave in here, what is the wavelength of that sound wave at omega star? So omega is equal to ck, right? This is what we would get for the sound waves. And so, and c could either be transverse or longitudinal. There are two sound speeds in this problem. And so I would get two different relationships here. And then this is equal to ct, or L, times 2 pi over L. Right? This is the wavelength of or I should say lambda. Okay. And then if I say if I ask, well, what is this at omega star? This gives me a length scale at the point that omega is equal to omega star, and I can define L longitudinal or L transverse from a relationship like this, once I know what omega star is and how it scales. And so this gives you two separate length scales, both of which diverge at this transition. And so you can see these length scales in a lot of other ways, and so there have been cutting arguments that Mathieu Vaillard introduced that give rise to lambda for the transverse length scale. There are other ways that you can see the transverse length scale, but this is the first way that we actually noticed that there was a length scale that appears in the problem, and it's the same scalings that you get here that you get for these other length scales. And so this, just to write this out, this is going to be, well, so this would be 2 pi CL over phi minus phi C omega star. And so then this is just going to be phi minus phi C to the alpha minus 2 over 2 divided by phi minus phi C to alpha minus 1 over 2. Okay, so this is what it happens to be for the longitudinal one, and you can work it out for the transverse one. What I'm doing here is I'm just plugging in what the speed of sound is, and the speed of sound just comes from the appropriate modulus over the density. So this m is the appropriate modulus. And I told you about the various moduli that we had and the scalings for those last time. So this is how you can get the various length scales, and both of these are going to diverge at the transition. Okay, and so this is the data for that you can actually see for the psi t, the lambda t, as a function of delta phi, and you can see that that's scaling. Okay, so now what I want to show is, okay, so what is the nature of these modes? And so these modes are clearly not plane waves. Okay, so how can I start to analyze what these things look like? So one way of just giving a gross feeling for this is something called the participation ratio. How many people have never heard of the participation ratio? Okay, so a bunch of you haven't heard of the participation ratio. So let me just describe what it is. It's saying if I have, I want to ask how many particles are actually contributing to any particular mode. Okay, and so how do I write that? The participation ratio is going to be the sum over all the particles of the amplitude of the mode on that site to the 4th power. This is in the denominator. And in the numerator, it's the sum over these amplitudes squared, all squared. Okay, so this is something that is just a number, right? It's got the same number of epsilons in it, so all those dimensions cancel out. And this is basically the normalization. It tells you, what the square of the wave function looks like, and this then is the dividing by epsilon to the 4th summed is what it gives you the participation ratio. So let's just look at this for a moment. So if epsilon were the same, just want to make sure whether I've calculated, kept the factor of 1 over n in here. Yeah, I should, the notation I have for n is a number of particles in the system. Okay, so if epsilon is the same for every particle in here, then I have n terms here. So for epsilon constant, I labels particles. So that is, it's the amplitude of that mode at a given frequency on that particle. So this is a function of the frequency of that particular normal mode frequency. I want to ask for that particular normal mode frequency how many particles are contributing. And so if this were constant, if all the modes contributed, all the particles contributed equally, this would be n times this thing, which is just sum of epsilon squared. So this is going to be n squared epsilon to the 4th divided by n. And this is going to be n terms here. So this is going to be n squared epsilon to the 4th. And so this is just 1. So if everything is contributing the same, the participation ratio is 1. That is, everything is doing the same thing. If epsilon is 1 on one particle only, and all the rest are 0, then what do we have? So all these, I get this thing to the 4th power only once. There's no n here, so this becomes p would then equal to 1. So this is going to be epsilon to the 4th there, and I'm going to get this epsilon to the 4th here. These sums don't give me any factors of n, so this is just 1 over n, and so this becomes just 1 over n. So the idea here is that depending on how many particles are actually participating in a mode, that's what I mean by participation ratio, I can go either between this region where only one particle is important, 1 over n, so it's really small, or all the way up to 1 where everything is equally contributing. Okay, is that good? So this is just a typical measure of wave functions or normal modes, whatever, to find out how big they are, how many particles are important in it.
I have a question. So this basically just gives a ratio of the particles. Like if epsilon is 1 on one particle, it basically means 1/n of particles are involved.
That's right.
So if I want to find the inverse participation ratio, would it be just like inverse of that?
Yeah. So it's just
but
the.
There would be n.
Yeah.
N particles are involved.
It's a ratio. So the inverse so this participation is 1 over n of the particles are involved, and the inverse of that is n. And so it's the inverse of that. So in the other case, it would have been 1, and so the inverse goes between 1 and n instead of 1 over n to.
No, I just want to know what the meaning of the inverse participation ratio would be. Is it the actual number of particles?
Well, this is the one that's the actual number of particles, right? So this is what it's saying. This is the number of particles that are doing it, and divided by n. And so it's the inverse of. I mean, I'm not quite sure how to.
So I think basically to find a number, we need to probably.
So I could have not.
Multiply this by n, because this is 1/n of particles.
That's right.
And we have n particles.
That's right.
1. In the top one, we have 1 times n.
Bn.
Okay.
That's right. So I could have. Yeah, that's another way of just. That's just a question of how you normalize this thing, and that's a.
Potentially very strongly frequency mode dependent.
And that's what I'm going to show in the next picture here.
Like Einstein model of a solid, you would get actually you would get 1
Yeah. That's right. So this is the participation ratio versus frequency for these jammed packings. And at some particular compression. And what I want you to see here is that there are two regions where the system is localized. So it's localized here at very high frequencies. That is, the participation ratio is 1 over n. It's getting really, really small. And what does that mean? Well, those are the normal high-frequency modes in a solid, which if you've got disorder, are going to be localized. It's just ordinary Anderson localization of particles going back and forth. The high-frequency ones are can't couple very well to the rest of the system. The density of states is small, so they don't overlap with other modes at the same frequency, and so they really become separated and they become localized. That's not the part of interest here, because that would have been true if I just put small amount of disorder into a crystal. But what's interesting is that down in this low frequency range, you also get very high degree of localization. That is, these particles too also have very low there are very few particles contributing to those very low frequency modes. And that's what's so unusual here. Now what Ludo was asking about was, well, do I see plane waves at low frequencies? And so this black line is our largest system that we're able to look at. And these peaks in there that you can see, peak here, here, and here, those are the plane waves that we're able to see below that frequency. And so you can see that those plane waves now become extended through the system. And so that's why you have those peaks, and between them, this thing tries to become quite localized. Okay, so this is one of the things. And so, saying that these modes that are at low frequencies are, first of all, there are a lot of these modes at low frequencies. The second is that the modes that are the very lowest frequencies are localized, quasi-localized. I mean, as I said last time, I'm uncomfortable with that word. I would have liked to call it highly resonant modes at the lowest frequencies. That is, they're really all the amplitude of the modes are concentrated on a few particles. But and so that's somehow suggesting that these modes can be dangerous in a system, that they can participate in a way that in the phenomena that you aren't typically expecting. And so here is one example of that. And so what did we look at here was, now that we have all the modes in the system, you can ask the following question. Suppose you have a mode just means that I'm in some parabolic minimum, right? This is it's a harmonic oscillator for a mode in this particular case, and the curvature of this is equal to the frequency of mode in there, right? That's all I'm trying to draw here. So this is kind of a potential energy versus the coordinate of that normal mode. What we can do now is, since we have all of these modes, I can take the system and I can just move it along this coordinate for some distance and then let go and ask what happens to this thing. And if I don't go too far, it'll just come back to where I started, right? It's just going to fall back down in that potential. But if I go a little bit too high, then I'm beginning to see a barrier into a next configuration, which is separated from this. It's not the same configuration anymore. So once I get a little bit over here, then, and I let this thing relax, it goes into a new configuration. And so you can ask, okay, what is the distribution of these barrier heights? Okay. And how does this is a mode-by-mode quantity. And this is what we see. So V max is what I should have called this. V max. Okay. So this is what we're plotting here versus the frequency for one given configuration. Well, a bunch of different configurations. Each of these are a different configuration, but it's as a function at one given compression. And what you see is that they're really correlated here. So they're even more dangerous than I started to tell you. That is, what this is saying is that the very lowest frequency modes are not only, a lot of them, not only are they localized, but they also have very, very small barriers against being kicked into a new state. So if you excite them, so if this is really the structure of a glass, then in a real system at low temperatures where we excite modes quantum mechanically, that is, the lowest frequencies get excited first, it's these modes which are going to be the dangerous ones to making this thing melt and go into a different state, or to go from one minimum to another. And so these are the modes that become important in that regime. And so this is really quite different from how we think of crystals. I'll get to just a second. So that in a crystal, typically you think that the most important modes for getting you into a different state would be the high frequency ones. That somehow that's where you're putting a lot of the energy. That's where these particles are smashing up into one another. Here, the picture is completely reversed. The dangerous modes are the very low frequency ones because they still have high K. That was what I was saying, that they still are a mixture of lots of components that are, where the particles are doing something with respect to its neighbor, not long wavelength behavior. So this is one thing. And these are the ones that are going to lead to instabilities. And so this is one thing that we hadn't expected for how glasses or jam systems would actually behave in a fundamentally different way from a crystal. Leo, you had a question.
Yeah, so there's doesn't have to be one of the completely two extremes, like one where it's completely extended and the other is localized at a point. What if they're localized in some submanifold, subspace of the volume? That's like
Some fractal measure. I mean, so what I've told you here with the participation ratio wouldn't have been able to distinguish that. So this is a poor man's version, or poor person's version, sorry, of how to actually look for localization. There are other ways of asking whether it's localized or whether it's extended but just in some fractal measure. And so I didn't tell you that if you actually look at what the modes look like down there, you actually see that a lot of them are actually localized. As on the sides of the systems that we're able to look at in simulations, they are localized. So we don't see that kind of structure particularly coming in.
Like some fourth chain or something like that. They're extended, but maybe localized.
Not that we can tell. Okay, so the last thing I just want to say here is that you can also ask about these modes. How anharmonic are they? So modes, as you excite a mode, if you excite it just a little bit, well, it should be a pure harmonic oscillation around its minimum. But there's always going to be some part of this which it mixes a cubic term or a quartic term into the potential. That this is not going to be a perfect parabola anymore. And so you can ask, well, how important is that? I mean, how strong is the anharmonicity of these different modes? And typically, the frequency shift, one way of measuring that is what is the frequency shift of a mode compared to its oscillation. So you know if you have a pendulum and you have a small amplitude, it doesn't, you get one frequency. But if you have a larger amplitude, well, the frequency shifts. And frequency shifts because you're mixing other terms into what that potential looks like. The sine theta is no longer just just theta anymore. It's got a theta cube term in it as well. And so the Gruneisen parameter is basically looking at that. This is a way of measuring what is the, well, you measure the frequency shift on a mode dependent on what the volume of the system is. So in this case, it would be with respect to the packing fraction. And so here you see that for all the high frequency modes above omega star, you get a relatively small Grunhausen parameter. That is, they're pretty harmonic. But once you get into this low frequency regime, then you get very highly anharmonic behavior. And so this is something which becomes kind of important if you're going to ask questions about, you know, what is the spectrum of these modes? That is, again, something that I'm not going to talk much about here, but there's a whole literature of low temperature properties of glasses which deal with the quantum mechanical two-level systems of glasses, and there's echo phenomena that are associated with that. The point about having a very strong anharmonic behavior in the tail is saying that these modes down here can also give rise to the same echoes that you could have gotten quantum mechanically, and therefore a lot of the statements that have been said about that picture are at least a little bit up for grabs. So, but I won't go into that here. Okay, so I'm going out of time, so I'm going to skip something. But yes, you have a question.
Could you define participation ratio as just E on the top and E squared on the bottom?
Well, you could do all sorts of things. I mean, each one will give you a different measure. I could have done epsilon to the squared to the cube on top and epsilon 6 on the bottom. And then they'll give you different numbers. Each of these things would be, they will give you different, so it's a you're just asking how, you have a distribution and you're looking at the different kurtosis. The different something about what the shape of that distribution is, and all of those different things will give you a different measurement of the shape. This is the simplest one, and it gives you one version. But you could have done this for any values, just as long as you have the same number of epsilons on the top as in the bottom. Well, so what we do is that when the way we do this is that we take our system, we know where all the position of the particles are, what all the interactions are. We can ask what is the full dynamical matrix of this system. That is, you know how all the particles interact. And so the dynamical matrix is just the set of equations that tell you how, to second order, how the particles are interacting with each other. So all we did was we diagonalized that matrix and got out what the eigenvalues are, which are each of the normal modes. And then from that, we just asked how big is the amplitude on each site.
So I'm comparing the extended modes versus the localized. Have you ever seen a set of localized modes where all the extended modes are just like a linear combination of that? I mean,
No, well, the point about the normal modes is that they're a complete basis set, orthonormal basis set for the system. So if I write this out in the way I've gotten for this distribution of things is that I have each mode is linearly independent of every other mode. And so once I've made this, and I don't have any degeneracies, this is, I can't take any linear combination, which is what you're asking. Okay, so so this is something about the nature of what this glassy state is, this jammed state is. And as I said beginning of last lecture, a lot has been left out. And so what has been left out is, I just had soft spheres, which are finite range repulsions, and that was all that I considered here. So you can ask, well, And so one thing that's been left out is long-range interactions. Right, that is, I haven't included those. And so those would be something that you would want to include in a model that if you're trying to look at what a glass looks like. Another thing would have been, a number of people asked this last time, how about including friction as a frictional interaction between the particles? A third thing would be, suppose I have attractions. Fourth would be, suppose I have three-body interactions. And where would that come into? Suppose I wanted to have a model that looked at a semiconducting glass where I have covalent bonds. Well, then I care about for this particle over here connected to me, I care about what this angle is, and that's a three-body interaction. And that's been left out of here. And so that would be an important thing to include. Temperature. And then one thing would be, I alluded to this last time, showing you why things weren't going to be so simple, so non-spherical. So all of these things have been left out of this simple model. I mean, this is really so idealized that it leaves all of these things out. And you can try to start including these different things. And people have tried to include various parts of this. And you know, what I would say is that this point J, where all, you know, this point phi C, where things just start to jam and get jammed, it contains new physics. It contains this physics of G over B going to 0. It contains a new physics of these, what the normal modes look like, and what these distributions of the normal modes look like. These are all new physics. And it also has to do with what is that transition as I go from unjammed to jammed as I just increase the density through that point. Each of those things you can ask, how did these, including these new things, change that? And they will, and you have to look at each one carefully, but a lot of that new physics still remains in one form or another in each of these different cases where people have looked at. Georgios. Well, it can be anything that's just not finite range. So Leonard-Jones is fine with me. Well, Leonard-Jones has attractions as well, but so I've included attractions here. So that would be Leonard-Jones. And so attractions plus long range would be a Leonard-Jones thing. So those are two separate things. But you could have had some long-range power law behavior, or just, you know, so that's the idea. Just have potentials that persist over a much larger distance. Pardon?
Would you have a system in mind?
Well, you can define, so 1 over r to the 12th.
What about the power laws?
What about?
Is there a real system that has power interactions?
Oh, a real system, I don't know, but there's certainly real systems that have long-range interactions. So that you could say that I have, you know, if there were dipoles on each of these particles, those would be have some long-range interaction, or charges, which would be really a messy thing. But those things would give rise to longer-range things. And so then if you put charged particles and charged colloid in liquid water, then you've got screening of this thing, and so you do have long-range interactions. Even they're repulsive, but they're purely repulsive, but they do have long-range parts to this, and don't particularly go to 0. Okay, so what I want to do now is I want to say, so what's this stuff good for? And I want to, let's see. Okay, this is what I'm skipping. I want to go to, whoops. Okay, I'm not, I want to just, so what is this good for? So I said I was going to tell you something about robots. And so this movie that I'm going to show you, which started right away, I was supposed to let you see it and then start it, but it's going to start right away, so I'm not going to. So what you're going to see is a robot, which there are two robots in this case, one of which is this thing that Heinrich Jaeger has called the universal gripper. And what it does is it's based on this idea of jamming. What does it do? So you take a bag filled with sand, a plastic, a balloon. Fill this balloon with sand, and then you go and you stick it over something, and it deforms, right? Because it's not jammed, it can flow all the way around. And then you pull a vacuum on it, and then it becomes hard as a rock. And once it's hard as a rock, it's conformed to this shape, and you can pull this thing up and do something with it. Okay, so this was the idea of using jamming as something actually a new form of robotics. And so this is, so that's the thing. It takes this shock absorber, not particularly light. It's able to pick it up. Then you let go, and each time you take that blue thing is what's filled with sand. Now you have an egg. It's raw, so it will break if you aren't careful. This hasn't broken. Now it lets it go. And you can see it was a raw egg. It was able to do so. You can be very gentle or strong enough to do this. Now you can pour water. Okay, so yeah, this is my favorite. You can write with it. So you can take this pen. Okay, so you can do lots of things with this. You can pick anything up with this, heavy things, light things without knowing what the shape is, and it's a very easy thing to do, and it's inexpensive. So it's something that you can do quite readily. This next thing is, well, you can make this thing walk by, you have all these little tubes filled with granular stuff that you can let relax or harden, relax and harden. And so now, let's see if, is this, so you can make something walk with this, just using this idea of jamming, unjamming transition, going through it over and over again. Okay, and it's a loose thing otherwise. And then this is not a movie, but just to show you, well, okay, you can actually use this for medical things. That is, if someone has a prosthesis, one of the things that is difficult is that the prosthesis really gives you problems where you're sticking it on, and this conforms to exactly what the shape is when you put it in. So it has that advantage as well. So these are some of the things that you get to do with the jamming. And I want to show this as this comes under the idea of what I was originally asked to talk about was experiments in marginality. So this is something that's a marginal system. You could not have done this with something that was not a marginal system. And this allows you a whole new set of degrees of freedom, which is, I think, really quite fascinating. Okay, so again, I'm going to skip some of this stuff. How do I lift this up? With an arrow up. Middle one. Okay. Well, I kind of did. That is, you have a rubber bag, a balloon. It's filled with sand, and it's filled with air and sand, and you can stick your finger into the thing, and the whole thing conforms to your finger, right? Because it's loose. But then once you suck the air out of that bag, the thing is jammed. By a little bit of pressure from the outside, these things are just hard sphere repulsion forces between these things with friction, but these things now are they're stuck in position. They can't move. It takes quite a bit of force to make to rearrange this the shape, and because of that, then once you have this thing, you can then use that to pull this thing up and move that. So that's what the.
Would you connect to what you were saying earlier? Is this still below 5C?
Oh, so I'm going through the transition. I'm starting off below 5C. That is, below 5C, it's unjammed, and I can put it down, and it conforms to the shape. And then I suck the air out, and now it's above 5C because there's some pressure on it. So because it has some pressure on it, now I'm above 5C, and I'm jammed. And so I'm going back and forth across that jamming threshold over and over again as I do each of these.
Barriers for, when you're above 5C, what is how strong is this?
That is, this is something that they would love to be able to have a great theory for. I don't think there is any particular theory for this. What you can do is, what they were asked to do by their funding agency was show that they can take a 2-gallon, a gallon jug of milk, pour something from it, and then lift up a baby. And they decided not to lift up the baby, but they just took an egg instead to do it. So that was the. So it goes between. Those are at least some of the limits, and whether you can design your granular material to be even stronger than that, that's something that you would like to do now, right? That is, you would like to find what is the ultimate shape. You don't want spheres anymore. You would like something that has something better than spheres to do this.
So is it better if they're like lighter than sand?
For this application, I don't care that they're necessarily lighter than sand because I got that big that can do it. But if you wanted to do something else, so we did something with a dance company where we had these things constructed of plastic bags with particles in them, and then the dancers could be having these things flopping around and then pull a vacuum on the thing, and then they become rigid for these dancers to interact with. So this was the idea behind this, and so there you would like them to be much lighter. Right, so that's so again, all these things are engineering questions now, but it's based on this principle of.
The egg, when the gripper goes on the egg, is less than half of the cover.
Yeah.
Even from free friction between the balloon or the egg or things like that.
Yeah. So part of the thing is actually what happens as you pull the vacuum, right? So does it. And so that was one thing they worried about, is once you've created such a nice contact there, how does it manage to hold this thing off? If it was really slippery, you might not be able to get a grip on it. But part of it is because you do have such a good contact that by pulling the vacuum on this, you've actually pulled a little bit of a vacuum inside here, and so there's a little bit of a vacuum around the egg top also that helps pull it down. So there are various things of this kind that. But this is an engineering question now, right? I mean, but it's again a simple idea that leads to doing this kind of engineering. Nachi.
Can the orbit say something about the shape of the object it's lifting?
Not particularly. That is something that we've wondered about, right? That is, can you somehow transmit forces from what you're putting down here to something else on top and give rise to some idea of what the shape is? And the answer is, it's not clear that you can, I think. I mean, it doesn't mean that it's impossible to, and maybe if you worked harder, we could figure out a way of doing it. But the simple things that have been looked at did not get that to work. Okay, so I'm way, I mean, this was supposed to be the first 5 minutes, so I'm way out of time. Okay, so what I want to talk about, I'm going to skip some things. I want to talk about rigidity. And okay, so rigidity, I mean, so what are the things that I would want to know about rigidity? So I've told you the two things. So I can talk about the bulk modulus. And what I'm doing there is I'm taking a d-dimensional object, whatever it is, and I'm squeezing it in all directions. And so I'm squeezing it in, and that's compression. And I'm asking what's the energy cost to do a compression of a certain amount. And so that's the first, I mean, that's how I would measure what the bulk modulus is. I can do the shear modulus. And there I take my cube and I distort it, at least in one of the shear moduli. I just do a simple shear by just shearing it in one direction. So I told you a little bit about how those things scaled in the jamming case. And I emphasized that G over B can be varied between 0 and wherever you're at. That is, wherever you start, you have a G over B, which is, they're comparable to one another. But if I'm in a jamming situation, I can move back towards the jamming threshold, and G over B can go all the way to 0. But why am I interested in G over B is because it really tells you what this thing new is. This is what's called the Poisson ratio. And for those of you who don't remember what the Poisson ratio is, I've got something here. So this is just an ordinary piece of material that if I pull on it in one direction, what's going to happen? It's going to shrink in these other directions. So here, you can watch it shrink, right? Okay. So that's a ordinary material that's got a positive Poisson ratio. Okay. But what would it mean to have a negative Poisson ratio? And that would be if you pull on the two sides, then it expands in the other two directions. So like this here. So this is something that has a negative Poisson ratio. Do you know of any materials that really have a negative Poisson ratio? Crumpled paper has, well, there's something that's kind of like a negative Poisson ratio there, but it's, well, okay, that qualifies, I would say. But where else do you know? Yes, so your wine bottles, you well, actually don't have a negative Poisson ratio. It's very close to 0 Poisson ratio. The point is, for a cork, if you want to push a cork into your wine bottle and stuff, you don't want it to expand. If you push it in and expands, which would be a positive Poisson ratio, it would crack the sides. And then if you pulled it out, it would be so easy to pull out, and so anything would make it move out. So you want something that has 0 Poisson ratio, and cork tree bark turns out to have a 0 Poisson ratio. But typically, negative. Oh, Patrick. Well, yes. So those things, but so there's that. But most of them are now just screw tops, and I wouldn't say a screw top is a negative Poisson ratio. It's a screw top. But yes, the plastic things that they do have that. I don't know about aerogels. I would have thought aerogels would be normal, but I don't know. I don't know this. Okay, so typically.
I was gonna say any like I'm cheating a little bit because I studied these objects, but like if you take a crinkled sheet of paper, a crinkled membrane, they have negative force separation.
Yeah, so that's what he said already. He already. Yeah. Okay, so basically, what my point is that you have to think hard to find some things that don't have a nice, robustly positive Poisson ratio, right? That is, most things are robustly positive, and then there are a few things which are classified officially as weird materials because they have a negative Poisson ratio. And this is clearly a highly engineered weird material, right? Okay. Okay, you can pass it around. That's what you're all waiting for that, right? I could tell. Yeah. Okay. The reason that what I want to say about here is that if I now look at the Poisson ratio as a function of G over B, and let me get it right. If this is 0, and this is -1, this is 1/2. So in 3 dimensions, the Poisson ratio is just a monotonic function of G over B. It goes between 1/2 when G is 0 and to -1 when B is 0. Right? That is, those are the 2 limits of this. And the question that we wanted to ask was, does disorder matter? Okay, so what I want to now just argue is, well, what would you have if you had a crystal? Okay, so I'm just properties of crystal. Now, I'm not going to say anything right away about nu for this, but I'm just asking, what do you think crystals do? And as I said at the very beginning of last lecture, what I'm really interested in is how are disordered systems, glasses, jam packings, and so forth, really different from a crystalline object. And so what I want to see is, okay, what would I expect in a crystal? So let me take a perfect crystal, 1 atom per unit cell. So I'm going to look at a simple crystal. And now I'm going to measure the bulk modulus. I get a value B. Now I'm going to reach into that crystal, and I'm going to grab some bond, I, and remove it. The bulk modulus is going to drop by a little bit, some delta BI. Right? Okay, so that was for removing that bond. And now replace that bond, and I do it again. I take some other bond out of the system, and what happens? I get a change in the bulk modulus, delta BI, but delta BJ. But delta BJ is the same as delta BI, right? Because all bonds are the same in the system. I could have done that for the shear modulus as well. That is, you pull out 1 atom or 1 bond in this network, and the shear modulus is going to drop, but it'll be dropped the same for whichever bond that you took out of the system. Okay, so you don't get much change between one particle or one bond and the next in a crystalline system. The other thing that you would guess is, okay, suppose I have some system that's a little bit more complicated, and I have a bulk modulus and a shear modulus in the system, and I find one bond which happens to have an abnormally large contribution to the bulk modulus, and I pull that one out. Okay, so I know the bulk modulus varied by as much as possible, but how about the shear modulus? And my naive guess, and this was just a naive guess, was, well, the shear modulus would also have changed more. Because if a bond is important, well, it's going to be important for all sorts of structural properties in the system. It's not just one thing. And so crystals are dull. Can't do too much with them. And so what do I mean by it? So I'm going to just draw out what I just said for you before. So I'm going to plot P of delta BI. So this is a probability of getting a change in the bulk modulus if I remove of some bond I. I'm going to plot this against delta BI divided by the average. Right, just so it's normalized. And what would I get here? Well, for the crystal, what I've just argued is I'm going to get a delta function. Okay. There's only one value of BI that's important. It's the average. It's the same for everything. And I could have done this for delta GI as well, and I would have had delta GI divided by. Right. So this is for both types of moduli. Okay. So what do I expect is going to happen when I put some disorder into the system? Well, again, what's my naive expectation? It's going to broaden, right? I mean, it's just so I would have gotten something that looks like this, perhaps, and that's what I expected this thing to look like.
Would the peak be at the same spot?
Well, it's on average, right? I've normalized this to be average, so I took that into account. Okay, so this is what I expected. So now I want to go and look at, well, what happened for a jam system? Okay, and see whether this is what we get. And in order to do this, I'm going to plot log. So you can see something is afoot, right? I mean, logs don't come unless there's a purpose to it. Okay, so what does the distribution of this look like for a jam system? This is what happened to the jam system. This was the crystal. It's very, very, very different, right? It's continuous and very broad. It goes as close to zero as we can measure in our simulations. So it's a very, very broad distribution of these contributions to this distribution function, to the bulk modulus or the shear modulus. And let me just. Pardon? Yeah, so I'm going to tell you what the shape of this whole curve is. So the shape of this curve is P of y. So whatever this y-axis is equal to 1 over square root 2 pi y to the minus 1/2 e to the minus y over 2. So, and this is true for the shear modulus, and it's also true, almost completely true for the bulk modulus. There's, in order to get the bulk modulus to have this, you have to take out something like 20 bonds in the system that we've looked at, and then it suddenly reverts to this universal curve. Okay, so this is a kind of a universal curve that comes out of this this behavior. And I mean, we understand some of the things about why it's that shape. I don't want to particularly bore you with that at the moment, but I want to just see what we can do with this. So this is what the shape of this curve is. It's the same for the bulk modulus and the shear modulus, basically, in the jam case. But now, suppose I take out a bond here that had the very, very largest contribution to the bulk modulus. And I asked, okay, so what did that do to the shear modulus? Well, my naive expectation before was that it should do a lot to the shear modulus. It doesn't. It doesn't care what it did to the bulk modulus. The shear modulus and the bulk modulus contributions of any bond are essentially completely decorrelated from each other. I mean, you calculate the Pearson coefficient is less than 1%. So they really don't care about each other. So in all ways, it's different from the crystal. That is, you get a broad distribution, goes all the way down to 0, and you don't and what one bond does to one modulus is irrelevant to what it does to the other modulus. Okay? So this makes you think, okay, so what can you do with this? Okay, so I'm going to plot G over B as a function of delta Z. That is, delta Z is just the excess coordination number over the jamming threshold. Okay? So if I look at this and I say, okay, I'm going to start off at some value of G over B, and I remove a bond at random, what's going to happen? Well, G and B are both going to drop, but the ratio is going to remain the same. This is just rigidity percolation. But suppose I don't do it that way. I don't remove bonds at random, but I go in and I say, okay, I'm going to remove the bond that has the largest contribution to the bulk modulus. So that means B in the denominator is getting as small as possible by the removal of that bond. And G only got smaller by some average amount. So that means G over B is going to increase. So now, I can put the logs here again. It starts to increase. And now I go back and I look at these distributions. The distributions don't change. The correlations don't change. So I do it again. And so I can change this ratio of G over B from order unity to 10 to the 12. I could have done the opposite. I could have taken away the largest bond contributing to the G. And then I would have come down on this thing. And so this goes down to -4. So I can get 16 orders of magnitude change in this ratio, G over B, by pruning appropriately. I could have done something different. I could have taken away the bond that contributed the least to G. Then taking away the one that goes least to G, G doesn't change, but B changes by the average amount, so this thing will go up not as fast. I could have taken the bond that was the least to B, and it would have likewise gone down, but not as fast.
So in order to do this, you started with a jam system and turned it into an elastic network.
Right.
What happens if you use a different random process for creating the elastic network?
So that's a great question. We've looked a little bit at this. These distribution functions that we get are kind of the same, so that you can use this for most disordered materials, we think. But then, you know, the advantage of saying we're starting with the jam thing is that we know what we're doing. Of saying we take any random network, I don't know how random you want to be. So what we have done is we started with a crystal and then took enough particles out so that it really became random. So it started with a crystal, and we were able to get similar types of behavior. But but it didn't start that way. That is, you had to really get to the random case before you start to do this. Okay, so this allows you to make all sorts of different materials, right? I mean, that's so if you start with a network, you can start removing bonds if you know what the bonds are doing, and then tune your network to have different kinds of auxetic properties. I should have said just negative is auxetic. That's just a word for negative Poisson ratio. Yeah.
So if I take a network, which is not a jam network, it's just some amorphous network, and I start taking out bonds that have the smallest contribution to change in the bulk modulus, but I don't care about the shear. Is it a way to go to the like isostatic state where the bulk modulus stays finite, so it kind of like behaves like a jam system?
Well, the thing that behaves most like a jam system in these 4 different cases that I told you about, and so is the one where I take away the thing with the largest bulk modulus. That has the same scaling as what we got in the jamming case. But is it really the same as, I mean, to what extent is it exactly the same? That's not quite clear. And there are issues with this. That is, you have to be careful here. That is, if you take out a bond that carries the most stress on it for, let's say, the bulk modulus, then when you remove that bond, it's going to redistribute that stress elsewhere in the system, particularly close to its neighbors. So that's why I wanted to make sure that we could do things by taking away the bond which is the least important, and you get the same kinds of behavior. So because you don't have that phenomenon going on. The other thing that happens is that, and so what that would mean is that you get a rupture, a crack forming in your system. The width of that crack actually depends on how close you are to the jamming threshold. So there's lots of stuff on this. I'm just trying to give you a flavor of what you can do with these systems. Okay, so this is something for the global properties. Okay. So could I do something for the local properties? Okay. Because these were the global properties, the bulk modulus and the shear modulus of the whole system. So here is something that we want to take a lesson from proteins. And this is something called allostery. And what does a protein do? I mean, one of the important things a protein does to regulate its behavior is if I have a protein object that looks like this, and over here I'm able to bind, let's say, an O2 molecule here that gets bound here. That opens up a slot here where I can now, far away in this molecule, where it can now react to the fact that this thing opened up, right? So that, and so this thing can now bind something which it couldn't bind unless this O2 was there. So this is how the protein typically regulates its behavior to be able to do things in the cell. That is, you want to put something here, and then this thing can act, and if you take this thing away, it can't act anymore. And so that's that would be an allosteric reaction, and it's local. That is, I'm doing something locally at one side of the system, and then far away, at a different part of the system, I'm asking for a response. Okay, so let's see, do I just say what I have anything here? Okay. Okay, so what I just wanted to say is, that, well, we're able to do this also. That is, if we look at this thing, because we have these amorphous systems, these systems based on jamming networks, by removing a small number of bonds, I'm able to get 100%, nearly 100% success rate in being able to tune in these interactions that we have. So let me, yeah, so this is the idea. So we have a network that looks like this. You put some force here, and you want to look there. And ask, am I able to make those things move apart the way I wanted to? So basically, the idea is, here we present you with this network, and ask, okay, which two sites would you like to be as your source? And so you tell me the blue ones, right?
Yeah.
She says the blue ones, and so these are our force, where we're choosing the forces. So we do this at random too, and now you want, where's the target? So the red ones. The red ones, okay, so the red ones are the target, okay? And then I ask you, do you want those particles to move apart or move together? And you get to choose. Apart, okay. So basically, it was random where we started, where we ended, and what we wanted the motion to be. So I can't do that here and design things on the spot, but we were able to do this. And what we did was we chose two sites at random, another two sites at random. They could be local, they could be spread out far away, and ask for that behavior. And ask, okay, so can we design that into the system? And the answer was yes, with nearly, this is at this kind of strain rate, we could get the response to be 4 times bigger than the applied strain by removing something on the order of 6 bonds. If you only wanted on the order of 1, that you only have to remove something like 3 bonds. So you can tune how much you want this response to be, and you can ask what the sign of the response should be. And the success rate is incredibly large as long as it's up to 1. I mean, we can hardly measure the failure rate. If you want 10 times bigger response, it's a few % failure rate where we couldn't make these things work. Okay, so this is something that we could do. And so what do we want to do from here? And so we're experimentalists. And so this is the picture they have. So I don't know if you can see this. So I have we make these networks now out of, we cut them out of with a laser cutter on a piece of rubber. And these are the networks that come out. And you see that I have 2 networks here, which if you come up afterwards, I can show you clearly. But these 2 networks are essentially the same, right? You can hardly see any difference. And if you come up, you will look and you'll see that I think there are 4 bonds that are different between these 2 networks, okay, if you look carefully. And then what we asked was, okay, we chose 2 points at random, which were these 2 points. And we wanted this point here to either come apart or go together. And so one of these, if I do this right, I don't know if I can do this standing up, but if I pull this, whoops. Can you see that? So I'm pulling it apart, and that V shape down there is coming together. Okay? So that's in one direction. And then for the other one, I pull and it comes apart. Okay? So we have so this is to show you in your face that we can actually manufacture these things in the lab, and these things are doable, and you can begin to think about how they may be a useful things to do. So we can do this in 3 dimensions. I think I had something here that showed 3 dimensions. So this was a 2-dimensional example. So we can build these things on a 3D printer and make 3-dimensional ones where you squeeze at one point and some other things move apart or together depending on what you've designed into this system. but these are experiments, right? And so there are things that go wrong with the experiments, and you learn something from what goes wrong with the experiments. And so that's why, again, part of this thing I want to say, these are experiments in marginality. So these are things that are, only doable because you're in this marginal system, and it tells you something about the nature of the ground states that you've gotten into. That is, these ground states that you fell into in this big potential well of all, not potential, but enormous landscape that you've been hearing about. And what you're told is, well, these wells, have certain statistical properties and so forth, and you've been told all about that. But one of the things that you weren't told is, well, this is one of the properties these things have. All of these wells that you get into can be tuned in this way. And that's something new. That's something different. And the other part about this is this network was one of the first we made, and it doesn't work so well. I mean, you have to look closely. It works. You convince yourself it works, but it's not in your face the way these work. And so what was different about here was, well, if you see the way this is done, there's bond bending forces here. Bond bending is not included in our jamming thing. Our jamming, these particles have no three-body interactions. This has three-body interactions now. That is, these things can't, it costs energy to distort, let's say, that bond there to make it move in and out. And that's something new in the system. And so what we have to do is try and figure out, well, first of all, what does that do to your system and when you put it in? And can you design a real mechanical system that gets rid of it? And so the system that we did was to use struts that look like this, that they're springs, basically, but at the edges, at the ends, where they attach to the nodes, they're much smaller, and so they're easier to bend in that angular way. And so that's, again, something that we learned from the experiments, and that the fact that you can actually do it is an important aspect of this. So what I want to just now say about this, so for this part of the so we're able to tune networks we can tune them because they're disordered and they're based on the jamming. We're able to tell you something about what these distribution functions are. We can make them in the lab. And so they're real things. They're not something so hard to think about that you can't actually get them. Let's see, is there anything else? And so this is saying that these disordered things are inherently different from crystals. And this you can tune both global and local. Okay. Okay. So this is a line that everyone should have in their talk, and this is called the bullshit line. So everything above this, you should believe what I said. Below this, it's up to you. Right? And so this is kind of what we hope you can do. But I think every talk should have a bullshit line. And if you don't have a bullshit line, you include too much bullshit earlier on. And so what is the things that I want to say? So where would we like to go with this? So what can you use these things for? So how about architecture? We no longer have architecture that's based just on rectangular units. I mean, you get all these funny networks that people like Gary makes. You know, it's what's his first name? Frank Gary. And you know, so what you can begin to think about is, well, can you put things into the architecture, make this network actually functional in some way? So why would you want to do that? Well, my favorite is that, you know, I have a colleague on the other side of the building from me who really irritates me. And so it wouldn't be nice if my building had this thing so that when he really irritates me, I can open up a little bit on my window and his window falls out. I mean, that would be the kind of thing that this is just made possible. Right? So that's one example. Another thing is aging. And I don't mean aging like us, we're all aging, but suppose I have a sand pile, and the sand pile is under a lot of weight. What was the idea behind all of this, the thing that was really triggering this? The thing that's triggering this is that if you had just done this blindly, what you would have thought is if you manipulate the forces between particles, or the struts between particles, or the strength of the interactions, you will affect everything more or less equally. So if you make something weaker, everything will be weaker. What this has said is no. If you attack those bonds which are actually under the most stress, you may have unexpected consequences. That is, the Poisson ratio, instead of being positive, could shrink to 0. Or go negative. I mean, you can change the properties by changing what you've done. So if you have your sand pile under a lot of weight, there are particles that are under a lot of force between them. Particles that are under a lot of force between them are going to, over time, plastically flow, which means that they are no longer going to have the same forces that I started. Those ones which had the most force are going to be the ones that are going to be changing the most. So you're changing something along the same lines as this, and will that give rise to new properties? Is this why road beds fail? Because something happened differently because things have been under stress for a long time, or dam collapses where it's basically just sand piles which suddenly get washed away. So this is an aging thing. Your body does this. I mean, there are things in your body which, in your bones in your legs, you have the trabecular bone, which is the stuff which is the tissue in the middle of the bone, and this, for more elderly people, is what gives a lot of strength to the bones. Well, the body knows how to look at those bonds which have been under most stress and make those stronger. But that's going to change something about the whole mechanical response of that object. And so these are things that you can ask about that biology actually knows how to do in some cases. One question is, well, what does this have to do with biology? And I have no idea. That is, we started off by thinking about this in terms of biology, right? This was where what gave us the idea to try and look at an allosteric kind of reaction. But we don't know whether biology uses it. All we can say is, gee, if biology uses it, because it's so easy to program into a material. We started off not knowing you could do this at all, and at the end found out it was trivial to do. You know, so that's one of the things. Whether that's useful for biology, I don't know, but that's one aspect of this. And then the other thing is, can you do this in situ? So do I need a computer to do this, or can I get the system to do it for itself, or measure it by itself? So can I put a system you know, so someone's here from Bob Behringer's lab. Yeah, and someone else too. So there was a few, yeah. And so what he has is this beautiful, or you guys have, is this beautiful photoelastic material. And so you could make a network out of the photoelastic material and try to see which bonds are under stress, and then do that for yourself, trying to figure out some way of manufacturing this to make these things have the properties that you want without having to go to the computer first. And also, could you do this at a microscopic level? Could I start off with a piece of glass that I now am able to, under pressure, put bonds between particles that are, when they're under a certain kind of pressure, I can take a laser and bash that bond so that they, they're disintegrated. And if that's the case, then maybe I can actually make materials this way, not just macroscopic networks. Okay, so my time is up for today, but I hope this just gives you a flavor of, oh, this opens up a door into a new kind of material manufacture that we didn't have before, and it's a big playground, and I hope you all come in. Okay, thanks.